such an application. When you look at individual materials, right, through data sheets, so handbooks and so on, they do not allow you to compare between different types of materials or different types of properties. And so this is a pain in terms of being able to come down to, for every new situation, a new way to search through that maze of 160,000 plus materials. And even if you did, after that, you don't know how you're going to translate that material into that given shape by a manufacturing process that's cost effective or can handle large quantities. So we look at two types of approaches. One is called a bar chart and the other one is called a property chart. This is an example, for instance, of a bar chart. Young's modulus plotted for all kinds. You'll see that they begin to group into different types of materials. Polymers end up having low modulus compared to metals that are high, and ceramics that can be high as well. Okay, and so these are all logarithmic scales, so there's quite a bit of range in all of this. And you come up with steels that, depending upon the concentration, again, the composition, you could have quite a bit of variation over like almost 2 orders of magnitude in terms of properties. You could also go to composites and make new things to fill up property ranges that are missing among these different traditional classes of materials. So you can get to something over here but sometimes you want not only modulus, but you want something else. You want it to be of low density as well. So here is an example of a modulus density plot. And again, you will see different classes of material get grouped into narrow areas. Polymers tend to be roughly around a density of 1. Metals, on the other hand, can be at least an order of magnitude higher, and this range can go all the way from magnesium alloys to tungsten alloy. In terms of the modulus, they can go from something that's very weak, such as a lead alloy, to something that is a tungsten alloy, which has much higher modulus. Again, look at the Young's modulus. It can go from elastomers all the way up to polyesters. Here are some natural materials stuck in as well. And at the top, in the yellow shaded bubble, are the family of materials which are ceramic, technical ceramics. And then you have composites thrown in over here. Okay, GFRP, glass fiber reinforced plastic, CFRP, carbon fiber. So for instance, in this plot, if you wanted a stiff material, you go to components that are at the top end of the plot. And so you see mostly they are metals, ceramics, and some composites. And some. If on the other hand you wanted something that was low density, then foams begin to dominate, polymers begin to dominate, composites give a combination, of lower density and a higher modulus increasingly, and woods are over here. And some ceramics come in as well, which low enough density but high enough modulus. So if you wanted to have a combination though of stiff and light, then basically you have materials that fall in this range over here. And so you have magnesium alloys close to this line, and aluminum alloys close to this line, maybe some titanium alloys over here. And surprisingly, a steel is not that far off to get this combination of properties, even though its density is about 8 times that of a plastic. Historically, how did we deal with selecting through these kinds of constraints? We only saw 2 properties. Imagine there are like at least 3 dozen different kinds of material properties to look into as we move forward into the next lecture. Right? So about 5,000 years ago, you basically had a lot of woods. You had some stone, some bone, maybe some pottery, and you had a gold. This was during the age where the pyramids were made, and they were made out of stone because they ended up being the strongest materials and most plentifully available, and they were light enough to be stacked up over here. And that was also no mean feat. How did they build all this without cranes and everything else? You can delve deeper into that. Fast forward into the Roman era, about 50 BC. So we've gone all the way from 3000 BC to about 50 BC, turn of the 2 millenniums ago. And so you have strength versus density plot now, and you begin to see that now you also have concrete, and so it could build temples. You had glass, and so you could end up having stained glass. You could build bricks, and so things happened. In addition, the number of metals and alloys that were available increased. And so you could have bronze and you could have wrought iron, and that could all help in construction of Roman temples. Fast forward another 1500 years roughly, and now you begin to see these medieval castles come up all over Europe, for instance. And you end up seeing that in addition to cast iron, you also have wrought iron, and then you have you have brick show up as well, and in addition you have more precious metals come in, which can option not just from being able to build things but also to fight for things, right? And so all these castles came along. The presence of the wrought iron also allowed for being able to defend those castles. And then you fast forward from there another 400 years, and you begin to see that you have now aluminum alloys, you have some different kinds of steels, and you begin to emerge different kinds of plastics come along. It's the Art Nouveau area. And then finally, you fast forward to uh, post World War II, and you begin to see this Chrysler building, for instance, in New York, which is the place I come from before I came here. You begin to see a lot more polymer options, a big range of metals, filling out a property space in terms of 4 orders of magnitude and density over an entire order. And then moving into present time, you have a lot more of the technical ceramics, a much greater range of composites and polymers, foams appearing for the first time, kinds of alloys that are becoming more and more specialized. So, from a design engineer's perspective, the job became a lot more complicated because how do you mix and match? It's great to have all this different property space filled out, okay, and then you still have holes over here. How do you decide what works and what doesn't work in this scenario where you have so many options? There are many ways to go wrong. Let's take even one of those plot, which is just aluminum alloys, right? One spec over here. This is fracture toughness plotted as against yield strength, and they all have similar fracture toughness over many different compositions, but the yield strength can vary over almost 2.5 orders of magnitude. It's a log plot. This is one kind of microstructure for copper aluminum alloys. If you go from then wrought alloys to casting alloys, the fracture toughness is lower, but then you can also be able to manufacture things differently, and you end up having a completely different microstructure, and it's possible by changing alloying elements to including silicon. So you change composition, you change the microstructure, you change the property scape, and you also not only properties in terms of the end use, but properties in terms of being able to manufacture them differently. So casting alloys, so basically the melting characteristics end up becoming very different.